Hello, this is Carlos Herrera, and this is problem number 3 for the extra credit for exam 2. So we have a reaction rate is 2,000 times faster. So this is already giving you the K1 and K2 faster at 42 degrees than at 8 degrees Celsius. So this is your T1 and your T2. It doesn't matter which one you pick, you just got to make sure that it corresponds to the same K values. So find the activation energy. So we're going to find the EA of the reaction. So I wrote down right here the equation you're going to use, which is Arrhenius's theory, which is the ln of K1 divided by K2 is equal to the activation energy, which we want to find over the rate, over the constant, which I wrote down here. You're going to have to remember it is 8.314 times T1 minus T2 divided by T1 times T2. So what do we have in the equation? What did the equation give us? So it gave us K1, which is we're going to use as 1 over K2, which we're going to do 2,000 since it's 2,000 times faster. And it gave well, we already know what R is, 8.314 joules per mole. Give me a second. And then they gave us T1, which is going to be the negative 8 degrees Celsius. But remember, we got to do it converted to Kelvin. So just add 273 degrees. And it should give you, what did I write down here? Once you plug it into your calculator, it's going to give you 265 degrees Kelvin. T2 is going to be 42 degrees Celsius plus the 273 degrees Kelvin. And it's going to give you 231 degrees Kelvin. And that's because this is negative, so you just plug whatever you have in. Ln of K1, which is 1 over 2,000, is equal to the EA, which we're trying to find, over 8.314 joules per mole, negative 1 second, times T1 265 minus 231 degrees times 265 231. So after you plug this all into your calculator and you manipulate it, the equation, your activation energy is gonna end up being 1.14 times 10 to the negative 5, and activation energy is always in joules. Thank you.